Dear students, in this chapter we are going to discuss about the dual nature of radiation and matter and also about the photoelectric effect and the de Broglie waves.
Dual nature of radiation and matter. Introduction. The Maxwell's equations of electromagnetism and Hertz experiments on the generation and detection of electromagnetic waves in 1887 strongly established the wave nature of light. Towards the same period at the end of 19th century, experimental investigations on conduction of electricity, electric discharge, through gases at low pressure in a discharge tube led to many historic discoveries. The discovery of X-rays by Röntgen in 1895, and of electron by J. Thomson in 1897, were important milestones in the understanding of atomic structure. It was found that at sufficiently low pressure of about 0.001 mm of mercury column, a discharge took place between the two electrodes on applying the electric field to the gas in the discharge tube. A fluorescent glow appeared on the glass opposite to cathode. The color of glow of the glass depended on the type of glass, it being yellowish-green for soda glass. The cause of this fluorescence was attributed to the radiation which appeared to be coming from the cathode. These cathode rays were discovered, in 1870, by William Crookes, who later, in 1879, suggested that these rays consisted of streams of fast-moving negatively charged particles. The British physicist, J. Thomson, 1856–1940, confirmed this hypothesis. By applying mutually perpendicular electric and magnetic fields across the discharge tube, J. Thomson was the first to determine experimentally the speed and the specific charge-to-mass ratio, E/m, of the cathode ray particles. They were found to travel with speeds ranging from about 0.1 to 0.2 times the speed of light, 3 times 10⁸ meters per second. The presently accepted value of E/m is 1.76 times 10⁻11 kilogram. Further, the value of E/m was found to be independent of the nature of the metal used as the cathode, emitter, or the gas introduced in the discharge tube. This observation suggested the universality of the cathode ray particles. Around the same time, in 1887, it was found that certain metals, when irradiated by ultraviolet light, emitted negatively charged particles having small speeds. Also, certain metals when heated to a high temperature were found to emit negatively charged particles. The value of E per meter of these particles was found to be the same as that for cathode ray particles. These observations thus established that all these particles, although produced under different conditions, were identical in nature. J. Thomson, in 1897, named these particles as electrons, and suggested that they were fundamental, universal constituents of matter. For his epoch-making discovery of electron, through his theoretical and experimental investigations on conduction of electricity by gases, he was awarded the Nobel Prize in Physics in 1906. In 1913, the American physicist R. A. Millikan, 1868–1953, performed the pioneering oil drop experiment for the precise measurement of the charge on an electron. He found that the charge on an oil droplet was always an integral multiple of an elementary charge, 1.602 times 10⁻−19 c. Millikan's experiment established that electric charge is quantized. From the values of charge, E, and specific charge, E/m, the mass, m, of the electron could be determined. Electron emission. We know that metals have free electrons, negatively charged particles, that are responsible for their conductivity. However, the free electrons cannot normally escape out of the metal surface. If an electron attempts to come out of the metal surface acquires a positive charge and pulls the electron back to the metal. The free electron is thus held inside the metal surface by the attractive forces of the ions. Consequently, the electron can come out of the metal surface only if it has got sufficient energy to overcome the attractive pull. A certain minimum amount of energy is required to be given to an electron to pull it out from the surface of the metal. This minimum energy required by an electron to escape from the metal surface is called the work function of the metal. It is generally denoted by phi naught and measured in eV, electron volt. 1 electron volt is the energy gained by an electron when it has been accelerated by a potential difference of 1 volt, so that 1 electron volt equals 1.602 times 10 power minus 19 J. This unit of energy is commonly used in atomic and nuclear physics. The work function, phi naught, depends on the properties of the metal and the nature of its surface. The minimum energy required for the electron emission from the metal surface can be supplied to the free electrons by any one of the following physical processes. I. Thermionic emission, by suitably heating, sufficient thermal energy can be imparted to the free electrons to enable them to come out of the metal. Field emission, by applying a very strong electric field, of the order of 10 power 8 volts per meter, to a metal, electrons can be pulled out of the metal, as in a spark plug. Photoelectric emission, when light of suitable frequency illuminates a metal surface, electrons are emitted from the metal surface. These light-generated electrons are called photoelectrons. Photoelectric effect, Hertz's observations. The phenomenon of photoelectric emission was discovered in 1887 by Heinrich Hertz, during his electromagnetic wave experiments. In his experimental investigation on the production of electromagnetic waves by means of a spark discharge, Hertz observed that high-voltage sparks across the detector loop were enhanced when the emitter plate was illuminated by ultraviolet light from an arc lamp. Light shining on the metal surface somehow facilitated the escape of free, charged particles which we now know as electrons. When light falls on a metal surface, some electrons near the surface absorb enough energy from the incident radiation to overcome the attraction of the positive ions in the material of the surface. After gaining sufficient energy from the incident light, the electrons escape from the surface of the metal into the surrounding space. Hallwach's and Leonard's observations. Wilhelm Hallwach's and Philip Leonard investigated the phenomenon of photoelectric emission in detail during 1886 to 1902. Leonard observed that when ultraviolet radiations were allowed to fall on the emitter plate of an evacuated glass tube enclosing 2 electrodes, metal plates, current flows in the circuit, figure 11.1. As soon as the ultraviolet radiations were stopped, the current flow also stopped. These observations indicate that when ultraviolet radiations fall on the emitter plate C, electrons are ejected from it which are attracted towards the positive, collector plate A by the electric field. The electrons flow through the evacuated glass tube, resulting in the current flow. Thus, light falling on the surface of the emitter causes current in the external circuit. Hallwach's and Leonard studied how this photocurrent varied with collector plate potential, and with frequency and intensity of incident light. Hallwach's, in 1888, undertook the study further and connected a negatively charged zinc plate to an electroscope. He observed that the zinc plate lost its charge when it was illuminated by ultraviolet light. Further, the uncharged zinc plate became positively charged when it was irradiated by ultraviolet light. Positive charge on a positively charged zinc plate was found to be further enhanced when it was illuminated by ultraviolet light. From these observations he concluded that negatively charged particles were emitted from the zinc plate under the action of ultraviolet light. After the discovery of the electron in 1897, it became evident that the incident light causes electrons to be emitted from the emitter plate. Due to negative charge, the emitted electrons are pushed towards the collector plate by the electric field. Hallwach's and Leonard also observed that when ultraviolet light fell on the emitter plate, no electrons were emitted at all when the frequency of the incident light was smaller than a certain minimum value, called the threshold frequency. This minimum frequency depends on the nature of the material of the emitter plate. It was found that certain metals like zinc, cadmium, magnesium, etc., responded only to ultraviolet light, having short wavelength, to cause electron emission from the surface. However, some alkali metals such as lithium, sodium, potassium, cesium and rubidium were sensitive even to visible light. All these photosensitive substances emit electrons when they are illuminated by light. After the discovery of electrons, these electrons were termed as photoelectrons. The phenomenon is called photoelectric effect. Experimental study of photoelectric effect. Figure 11.1 depicts a schematic view of the arrangement used for the experimental study of the photoelectric effect. It consists of an evacuated glass, quartz tube having a thin photosensitive plate C and another metal plate. A monochromatic light from the source S of sufficiently short wavelength passes through the window W and falls on the photosensitive plate C, emitter. A transparent quartz window is sealed onto the glass tube, which permits ultraviolet radiation to pass through it and irradiate the photosensitive plate C. The electrons are emitted by the plate C and are collected by the plate A, collector, by the electric field created by the battery. The battery maintains the potential difference between the plates C and A, that can be varied. The polarity of the plates C and A can be reversed by a commutator. Thus, the plate A can be maintained at a desired positive or negative potential with respect to emitter C. When the collector plate A is positive with respect to the emitter plate C, the electrons are attracted to it. The emission of electrons causes flow of electric current in the circuit. The potential difference between the emitter and collector plates is measured by a voltmeter, V, whereas the resulting photocurrent flowing in the circuit is measured by a micrometer. The photoelectric current can be increased or decreased by varying the potential of collector plate A with respect to the emitter plate C. The intensity and frequency of the incident light can be varied, as can the potential difference V between the emitter C and the collector A. We can use the experimental arrangement of figure 11.1 to study the variation of photocurrent with a. Intensity of radiation, b. Frequency of incident radiation, c. The potential difference between the plates A and C, and d. The nature of the material of plate C. Light of different frequencies can be used by putting appropriate colored filter or colored glass in the path of light falling on the emitter C. The intensity of light is varied by changing the distance of the light source from the emitter. Effect of intensity of light on photocurrent. The collector A is maintained at a positive potential with respect to emitter C so that electrons ejected from C are attracted towards collector A, keeping the frequency of the incident radiation and the potential fixed. The intensity of light is varied and the resulting photoelectric current is measured each time. It is found that the photocurrent increases linearly with intensity of incident light as shown graphically in figure 11.2. The photocurrent is directly proportional to the number of photoelectrons emitted per second. This implies that the number of photoelectrons emitted per second is directly proportional to the intensity of incident radiation. Effect of potential on photoelectric current. We first keep the plate A at some positive potential with respect to the plate C and illuminate the plate C with light of fixed frequency μ and fixed intensity I1. We next vary the positive potential of plate A gradually and measure the resulting photocurrent each time. It is found that the photoelectric current increases with increase in positive, accelerating, potential. At some stage, for a certain positive potential of plate A, all the emitted electrons are collected by the plate A and the photoelectric current becomes maximum or saturates. If we increase the accelerating potential of plate A further, the photocurrent does not increase. This maximum value of the photoelectric current is called saturation current. Saturation current corresponds to the case when all the photoelectrons emitted by the emitter plate C reach the collector plate A. We now apply a negative, retarding, potential to the plate A with respect to the plate C and make it increasingly negative gradually. When the polarity is reversed, the electrons are repelled and only the sufficiently energetic electrons are able to reach the collector A. The photocurrent is found to decrease rapidly until it drops to zero at a certain sharply defined, critical value of the negative potential V0 on the plate A for a particular frequency of incident radiation. The minimum negative, retarding, potential V0 given to the plate A for which the photocurrent stops or becomes zero is called the cutoff or stopping potential. The interpretation of the observation in terms of photoelectrons is straightforward. All the photoelectrons emitted from the metal do not have the same energy. Photoelectric current is zero when the stopping potential is sufficient to repel even the most energetic photoelectrons, with the maximum kinetic energy, Kmax, so that Kmax equals EV0. We can now repeat this experiment with incident radiation of the same frequency but of higher intensity I2 and I3. We note that the saturation currents are now found to be at higher values. This shows that more electrons are being emitted per second, proportional to the intensity of incident radiation. But the stopping potential remains the same as that for the incident radiation of intensity I1, as shown graphically in figure 11.3. Thus, for a given frequency of the incident radiation, the stopping potential is independent of its intensity. In other words, the maximum kinetic energy of photoelectrons depends on the light source and the emitter plate material, but is independent of intensity of incident radiation. Effect of frequency of incident radiation on stopping potential. We now study the relation between the frequency nu of the incident radiation and the stopping potential V0. We suitably adjust the same intensity of light radiation at various frequencies and study the variation of photocurrent with collector plate potential. The resulting variation is shown in figure 11.4. We obtain different values of stopping potential but the same value of the saturation current for incident radiation of different frequencies. The energy of the emitted electrons depends on the frequency of the incident radiations. The stopping potential is more negative for higher frequencies of incident radiation. Note from figure 11.4 that the stopping potentials are in the order V03 greater than V02 greater than V01 if the frequencies are in the order nu3 greater than nu2 greater than nu1. This implies that greater the frequency of incident light, greater is the maximum kinetic energy of the photoelectrons. Consequently, we need greater retarding potential to stop them completely. If we plot a graph between the frequency of incident radiation and the corresponding stopping potential for different metals, we get a straight line, as shown in figure 11.5. The graph shows that the stopping potential V0 varies linearly with the frequency of incident radiation for a given photosensitive material. There exists a certain minimum cutoff frequency nu0 for which the stopping potential is 0. These observations have two implications. The maximum kinetic energy of the photoelectrons varies linearly with the frequency of incident radiation, but is independent of its intensity. For a frequency nu of incident radiation, lower than the cutoff frequency nu0, no photoelectric emission is possible even if the intensity is large. This minimum, cutoff frequency nu0, is called the threshold frequency. It is different for different metals. Different photosensitive materials respond differently to light. Selenium is more sensitive than zinc or copper. The same photosensitive substance gives different response to light of different wavelengths. For example, ultraviolet light gives rise to photoelectric effect in copper while green or red light does not. Note that in all the above experiments, it is found that, if frequency of the incident radiation exceeds the threshold frequency, the photoelectric emission starts instantaneously without any apparent time lag, even if the incident radiation is very dim. It is now known that emission starts in a time of the order of 10⁻⁹s or less. We now summarize the experimental features and observations described in this section. For a given photosensitive material and frequency of incident radiation, above the threshold frequency, the photoelectric current is directly proportional to the intensity of incident light, figure 11.2. For a given photosensitive material and frequency of incident radiation, saturation current is found to be proportional to the intensity of incident radiation, whereas the stopping potential is independent of its intensity, figure 11.3. For a given photosensitive material, there exists a certain minimum cutoff frequency of the incident radiation, called the threshold frequency, below which no emission of photoelectrons takes place, no matter how intense the incident light is. Above the threshold frequency, the stopping potential, or equivalently the maximum kinetic energy of the emitted photoelectrons, increases linearly with the frequency of the incident radiation, but is independent of its intensity, figure 11.5. The photoelectric emission is an instantaneous process without any apparent time lag, approximately 10⁻⁹ second or less, even when the incident radiation is made exceedingly dim. Photoelectric effect and wave theory of light. The wave nature of light was well established by the end of the 19th century. The phenomena of interference, diffraction and polarization were explained in a natural and satisfactory way by the wave picture of light. According to this picture, light is an electromagnetic wave consisting of electric and magnetic fields with continuous distribution of energy over the region of space over which the wave is extended. Let us now see if this wave picture of light can explain the observations on photoelectric emission given in the previous section. According to the wave picture of light, the free electrons at the surface of the metal, over which the beam of radiation falls, absorb the radiant energy continuously. The greater the intensity of radiation, the greater are the amplitude of electric and magnetic fields. Consequently, the greater the intensity, the greater should be the energy absorbed by each electron. In this picture, the maximum kinetic energy of the photoelectrons on the surface is then expected to increase with increase in intensity. Also, no matter what the frequency of radiation is, a sufficiently intense beam of radiation, over sufficient time, should be able to impart enough energy to the electrons, so that they exceed the minimum energy needed to escape from the metal surface. A threshold frequency, therefore, should not exist. These expectations of the wave theory directly contradict observations I, E, and E, given at the end of subsection 11.4.3. Further, we should note that in the wave picture, the absorption of energy by electron takes place continuously over the entire wavefront of the radiation. Since a large number of electrons absorb energy, the energy absorbed per electron per unit time turns out to be small. Explicit calculations estimate that it can take hours or more for a single electron to pick up sufficient energy to overcome the work function and come out of the metal. This conclusion is again in striking contrast to observation, IV, that the photoelectric emission is instantaneous. In short, the wave picture is unable to explain the most basic features of photoelectric emission. Einstein's photoelectric equation, energy quantum of radiation. In 1905, Albert Einstein (1879–1955) proposed a radically new picture of electromagnetic radiation to explain photoelectric effect. In this picture, photoelectric emission does not take place by continuous absorption of energy from radiation. Radiation energy is built up of discrete units, the so-called quanta of energy of radiation. Each quantum of radiant energy has energy h nu, where h is Planck's constant and nu the frequency of light. In photoelectric effect, an electron absorbs a quantum of energy hnu of radiation. If this quantum of energy absorbed exceeds the minimum energy needed for the electron to escape from the metal surface, work function phi 0, the electron is emitted with maximum kinetic energy. Kmax equals h nu, phi 0. More tightly bound electrons will emerge with kinetic energies less than the maximum value. Note that the intensity of light of a given frequency is determined by the number of photons incident per second. Increasing the intensity will increase the number of emitted electrons per second. However, the maximum kinetic energy of the emitted photoelectrons is determined by the energy of each photon. Equation 11.2 is known as Einstein's photoelectric equation. We now see how this equation accounts in a simple and elegant manner all the observations on photoelectric effect given at the end of subsection 11.4.3. According to equation 11.2, Kmax depends linearly on nu and is independent of intensity of radiation, in agreement with observation. This has happened because in Einstein's picture, photoelectric effect arises from the absorption of a single quantum of radiation by a single electron. The intensity of radiation, that is proportional to the number of energy quanta per unit area per unit time, is irrelevant to this basic process. Since Kmax must be non-negative, equation 11.2 implies that photoelectric emission is possible only if h nu greater than phi 0 or nu greater than nu 0, where nu 0 is equal to phi 0 by h. Equation 11.3 shows that the greater the work function phi 0, the higher the minimum or threshold frequency nu needed to emit photoelectrons. Thus, there exists a threshold frequency nu 0 equals phi 0 per hour for the metal surface, below which no photoelectric emission is possible, no matter how intense the incident radiation may be or how long it falls on the surface. In this picture, intensity of radiation as noted above, is proportional to the number of energy quanta per unit area per unit time. The greater the number of energy quanta available, the greater is the number of electrons absorbing the energy quanta and greater, therefore, is the number of electrons coming out of the metal, for nu greater than nu 0. This explains why, for nu greater than nu 0, photoelectric current is proportional to intensity. In Einstein's picture, the basic elementary process involved in photoelectric effect is the absorption of a light quantum by an electron. This process is instantaneous. Thus, whatever may be the intensity, that is the number of quanta of radiation per unit area per unit time, photoelectric emission is instantaneous. Low intensity does not mean delay in emission, since the basic elementary process is the same. Intensity only determines how many electrons are able to participate in the elementary process, absorption of a light quantum by a single electron, and, therefore, the photoelectric current. Using equation 11.1, the photoelectric equation 11.2, can be written as EV0 equals h nu, phi 0. For nu greater than or equal to nu 0, now we get the equation 11.4. This is an important result. It predicts that the V0 versus nu curve is a straight line with slope equals h by e. Independent of the nature of the material. During 1906 to 1916, Millikan performed a series of experiments on photoelectric effect, aimed at disproving Einstein's photoelectric equation. He measured the slope of the straight line obtained for sodium, similar to that shown in figure 11.5. Using the known value of E, he determined the value of Planck's constant h. This value was close to the value of Planck's constant, equals 6.626 times 10 power minus 34 joules second, determined in an entirely different context. In this way, in 1916, Millikan proved the validity of Einstein's photoelectric equation, instead of disproving it. The successful explanation of photoelectric effect using the hypothesis of light quanta and the experimental determination of values of h and phi 0, in agreement with values obtained from other experiments, led to the acceptance of Einstein's picture of photoelectric effect. Millikan verified photoelectric equation with great precision, for a number of alkali metals over a wide range of radiation frequencies. Particle nature of light, the photon. Photoelectric effect thus gave evidence to the strange fact that light in interaction with matter behaved as if it was made of quanta or packets of energy, each of energy h nu. Is the light quantum of energy to be associated with a particle? Einstein arrived at the important result, that the light quantum can also be associated with momentum, h nu by c. A definite value of energy as well as momentum is a strong sign that the light quantum can be associated with a particle. This particle was later named photon. The particle-like behavior of light was further confirmed, in 1924, by the experiment of A. H. Compton, 1892–1962, on scattering of X-rays from electrons. In 1921, Einstein was awarded the Nobel Prize in Physics for his contribution to theoretical physics and the photoelectric effect. In 1923, Millikan was awarded the Nobel Prize in Physics for his work on the elementary charge of electricity and on the photoelectric effect. We can summarize the photon picture of electromagnetic radiation as follows. In interaction of radiation with matter, radiation behaves as if it is made up of particles called photons. Each photon has energy E equals h nu, and momentum p equals h nu by c, and speed c, the speed of light. All photons of light of a particular frequency nu, or wavelength lambda, have the same energy E and momentum p, whatever the intensity of radiation may be. By increasing the intensity of light of given wavelength, there is only an increase in the number of photons per second crossing a given area, with each photon having the same energy. Thus, photon energy is independent of intensity of radiation. Photons are electrically neutral and are not deflected by electric and magnetic fields. In a photon-particle collision, such as photon-electron collision, the total energy and total momentum are conserved. However, the number of photons may not be conserved in a collision. The photon may be absorbed or a new photon may be created.
Hello, I am Albert Einstein. The photoelectric effect discovered in 1905 revolutionized our understanding of light and matter interaction. It shows that when light of a certain frequency hits a material surface, electrons are emitted.
Can a beam of light act like a bunch of tiny particles? Einstein said yes, and it changed physics. In 1905, Einstein explained the photoelectric effect. Shine light on certain metals and electrons get ejected, but only if the light has enough energy. Einstein proposed light comes in packets called photons. Each has energy proportional to its frequency, E, H, F. Higher frequency means more energetic photons that can knock electrons free. Increasing brightness just sends more photons, not more energy, per photon. That simple idea solved puzzling experiments and confirmed the quantum nature of light. It also won Einstein the Nobel Prize and paved the way for solar cells' photodetectors' modern quantum tech. Look at the picture of Einstein and the equation E charge HF. Tiny packets, huge consequences. Quick, grab that curiosity and go read more. Science gets cooler the deeper you look.
Wave nature of matter. The dual, wave-particle, nature of light, electromagnetic radiation, in general, comes out clearly from what we have learnt in this and the preceding chapters. The wave nature of light shows up in the phenomena of interference, diffraction and polarization. On the other hand, in photoelectric effect and Compton effect, which involve energy and momentum transfer, radiation behaves as if it is made up of a bunch of particles, the photons. Whether a particle or wave description is best suited for understanding an experiment depends on the nature of the experiment. For example, in the familiar phenomenon of seeing an object by our eye, both descriptions are important. The gathering and focusing mechanism of light by the eye lens is well described in the wave picture. But its absorption by the rods and cones of the retina requires the photon picture of light. A natural question arises: if radiation has a dual, wave-particle, nature, might not the particles of nature, the electrons, protons, etc., also exhibit wave-like character? In 1924, the French physicist Louis-Victor de Broglie, pronounced as de Broglie, 1892–1987, put forward the bold hypothesis that moving particles of matter should display wave-like properties under suitable conditions. He reasoned that nature was symmetrical and that the two basic physical entities, matter and energy, must have symmetrical character. If radiation shows dual aspects, so should matter. De Broglie proposed that the wavelength lambda associated with a particle of momentum p is given by the equation 11.5, where m is the mass of the particle and v its speed. Equation 11.5 is known as the de Broglie relation, and the wavelength lambda of the matter wave is called de Broglie wavelength. The dual aspect of matter is evident in the de Broglie relation. On the left-hand side of equation 11.5, lambda is the attribute of a wave, while on the right-hand side the momentum p is a typical attribute of a particle. Planck's constant h relates the two attributes. Equation 11.5 for a material particle is basically a hypothesis whose validity can be tested only by experiment. However, it is interesting to see that it is satisfied also by a photon. For a photon, as we have seen, p equals h nu by c. Therefore, h by p equals c by nu equals lambda. That is, the de Broglie wavelength of a photon given by equation 11.5 equals the wavelength of electromagnetic radiation of which the photon is a quantum of energy and momentum. Clearly, from equation 11.5, lambda is smaller for a heavier particle, large m, or more energetic particle, large v. For example, the de Broglie wavelength of a ball of mass 0.12 kilograms moving with a speed of 20 meters per second is easily calculated. This wavelength is so small that it is beyond any measurement. This is the reason why macroscopic objects in our daily life do not show wave-like properties. On the other hand, in the subatomic domain, the wave character of particles is significant and measurable.
Hi, I am de Broglie. I am going to tell you about the matter waves.
Why do 100% of electrons behave like both particles and waves? What if matter itself ripples through reality? Let me explain how I discovered the wave nature of everything. Bonjour. I am Louis de Broglie. In 1924, I asked a radical question. If light can be both a wave and a particle, why not matter too? Imagine, every object a tiny electron, your morning croissant has a wave hidden inside it. Wild, right? This idea is now called the de Broglie hypothesis. It means particles are not just little marbles. Sometimes they act like waves, spreading out and interfering, just like ripples in a pond. My theory was first met with skepticism, but soon, thanks to experiments with electrons, scientists saw those mysterious matter waves in action. This changed quantum physics forever. Suddenly, the whole universe was dancing to a hidden wavy rhythm. So next time you look at anything, your hand, your coffee, your cat, remember, it's not just matter, it's waves too. The universe, it's stranger and more beautiful than you ever imagined.
When on Earth, a hummingbird dances. Its wings flutter with a speed that to our eyes and to our camera recording equipment appear nothing more than a blur. We know the wings are there, yet they oscillate with such rapidity that they elude our full comprehension. Only when the moment is captured with a high-speed camera do they reveal their real behavior. At the scale of the unimaginably minute, we find the atom. Around its nucleus heart, electrons dance in a manner reminiscent of the hummingbird wing, a kind of probabilistic blur known as an electron cloud, seemingly unknowable in their speed and journey until scientists